When solving an equation, you can get an answer something like x equals 3. So that's your final answer, and to plot it, you would just do a closed circle on that 3 to denote that 3 is a solution to that equation. But if you have an inequality, let's say x is greater than or equal to 3, you would be like 3, 4, 5, but you'd also have to say like 3.678, right? So there are unlimited values that are greater than or equal to 3, including all of those decimal pieces. So every value that we listed there, bigger than 3, including the decimal pieces, would all be included in the solution. And when you have these so close together, these closed circles, they sometimes, or they kind of form a line. The question you want to ask yourself is what happens close to your boundary point? The boundary point for this problem is 3. So what happens close to 3 if you're looking for all x values greater than or equal to 3? So the question you want to ask yourself, is 3 a solution? Is 3 greater than or equal to 3? That is a true statement, which means 3 would be a solution. So you'd have a closed dot on 3, and it would be all the values greater than or equal to 3. So this would be your graph, and you would want to also write your final answer in interval notation. To get your interval notation, you're going to look at your graph from left to right. There are no values over here that make it true. The first value that makes it true is 3. Your boundary point, you have to ask yourself if your boundary point is included or not included. If it's included, like in this case, you would have a closed bracket, and it would go all the way up to infinity. For infinity and negative infinity, you will always have this open parenthesis here. If the symbol became just x is greater than 3, it would be a very similar solution. All of these values would still work, so you'd still shade to the right, but at your boundary point, it wouldn't work because 3 is not greater than 3. So that means your boundary point would not work, so you would have an open circle there. The reason you have an open circle is because 3.00001 works. So if I were to actually graph it, it looks like it would cover it. But it's an open circle to denote that you get infinitely close to 3 without reaching that specific value. To denote that in interval notation, instead of using a closed bracket, you would use an open parenthesis. So it would go from 3 to infinity. This would be the interval notation for this inequality and this graph. So we'll use this symbol when your boundary point is included. That usually will look something like this in inequality form. And that's when your boundary point is closed or included. If it's not included, you'll use this open parenthesis, and you'll typically see that in these types of scenarios. That's when your boundary point is open. It gets infinitely close to the boundary point, but doesn't reach it. See if you can write the inequality for example 1, and then check your answer with mine. X is greater than negative 1. Now we're going to try to sketch our solution set on a graph. So our boundary point is negative 1. Will our boundary point be open or closed? It will be open because it's just greater than. We're only shading values where they are true. So is negative 1 greater than negative 1? No, but negative 0.9999 is. So we're going to shade to the right for this solution here. If I were to try any of these x values over here, for example 0, and I were to plug that in wherever I see an x in the inequality, I should be left with a true statement. 0 is greater than negative 1. That's a true statement, so I should shade where it is true. Try to pause the video here and write the interval notation. There is nothing over here that makes the inequality true. The first value that you need to look at is negative 1. Negative 1 would not be included, but infinitely close would be. So we want to denote that with an open parenthesis. And all of the values from then on, so it goes all the way up to infinity. And remember, on infinity and negative infinity, it will always be open. See if you can write all 3 forms of the solution to example 2. Play the video when you're ready. X is less than or equal to negative 1.7. For this equation, the boundary point would be negative 1.7, and it would be included because negative 1.7 is less than or equal to negative 1.7 because of this or equal to piece to your inequality. And we are going to shade all values where they are true. So all values less are to the left. To write your interval notation, you always read your graph from left to right. So what is this value all the way to the left of your graph? Well, you're approaching negative infinity. If you were approaching all the way to the right, you'd be approaching positive infinity. So we read it from left to right because our interval notation always has to be in numerical order. And remember, for infinity and negative infinity, we are always open. So negative infinity up to negative 1.7. And should negative 1.7 be open or closed? Closed because the boundary point is included. So here is your interval notation. If you encounter more than one inequality combined with a word, the words you will typically be looking for are and or. If the word is and, that implies both must be true. So and is for an intersection. We use that symbol to help us denote intersection. That means where both sets are true. So the intersection of two sets is true if both sets are true at those values. If the word connecting them is or, that's the union of two sets, and that union will be true if at least one set is true. For example 3, we're going to need a working graph. So I'm going to draw my working graph down here. I need all the values that are greater than or equal to 0 and also less than 9. So let's start with that first part. Greater than or equal to 0 would be closed and to the right. Less than 9 would be open on 9 and all the values to the left. And is the intersection, which means both sets must be true. So we look all the way to the left of our graph. Only the yellow one is true over here. They both are true on 0. And they're both true in the middle. And they're both true at 8.9999999, but they're not both true on 9. So they're infinitely close to 9 and true. How do we denote that? They're both true on 9. They're both true on 0, so it'll be closed on 0. And only one is true on 9, but they're both true infinitely close. So this would be our final graph, because only the orange is true from then on. Once you get your graph, you can read your graph from left to right to get your interval notation. See if you can pause the video here and try to get your interval notation on your own. The interval notation would go from 0 closed up to 9 open. If you were to write your inequality, you can write that in two ways. It says x is greater than or equal to 0 and x is less than 9. If the word connecting the two inequalities is and, you can condense that form a little bit further and you can recopy the inequality with the larger value on the right. And then look at this first inequality. The x has to be greater than or equal to the 0. So the x would still have to be greater than or equal to the 0. So notice how I'm reading this backwards. X is greater than or equal to 0. You are allowed to condense your inequality in this form when the word connecting them is and. X does not equal 2 and x does not equal 4. So this would take a working graph and a final graph to figure out my solution. Not equal to 2 means you could be bigger or less. You could be 1.99999 or 2.0000001, right? Infinitely close, just not exactly 2. Same with 4. You could be bigger or smaller. And implies where are they both true? So they're both true over here, but not on 2. They're both true in the middle, but not on 4. And they're both true on the right-hand side. This would be your final graph. Now I'm going to read my graph from left to write the interval notation. If you ever get more than one set of numbers that don't have any sets in common, so they're kind of disconnected, they have no elements in common, they're disjoint, you would connect them with the union symbol. So as I read this graph from left to right, it would be from negative infinity to 2, open, union, 2 to 4, open, union, 4 to infinity. This would be the interval notation for this set. X is less than or equal to negative 2, or X is greater than 3. Greater than 3, less than or equal to negative 2. Now, if I look at these words connecting them, I see the word or. Or is the union where at least one set is true. So if at least one set is true, the union is true. So at least one set is true over here, the first set. And at least one set is true over here. So the working graph for this problem and the final graph are actually exactly the same. I don't have to rewrite anything here. I can just read my graph from left to right to get the interval notation. So I would start at negative infinity and go up to negative 2 closed. Now there's no common elements, so I have to use a union symbol between them. And I start at 3, infinitely close to 3 but not reaching 3 would be open, all the way up to infinity. So this would be my interval notation. X is greater than or equal to 0, or X is less than 9. This is reminding me of the problem above, except the word connecting them is now or. So my working graph should look exactly the same as my working graph from before. Less than 9 and greater than or equal to 0. If I'm looking for or, I'm looking for at least one set to be true. If at least one set is true, the union is true. So over here, the orange set is true. So that means this should be on my graph. Then I get to 0. Both are true on 0, so or is definitely true. And both are true in the middle, so or is definitely true. The next place I look at is 9. Is at least one set true on 9? Yeah, the yellow set is true. So we're good on 9, and we're good forevermore because the yellow set continues to be true. So this is your working graph, and this is your final graph. So as you can see on the final graph, we have from negative infinity to positive infinity. So the union of these two sets is actually all real numbers. If you are ever looking for the intersection of two sets that go in opposite directions, for example, numbers less than 1 and also greater than or equal to 3, if you're looking for the intersection or the and, where are they both true, they're actually never both true. So this graph for the final result would be empty, it would be a blank graph, and there would be no real solution. So if you look for the intersection between two sets that are disjoint, you will get no solution. See if you can pause the video and graph the inequalities. Remember, what word is assumed if you can condense it in this manner? The word is and. Once you graph it, can you write the interval notation? Try A and B. X is greater than 0. So you see how I have to read that backwards? X is greater than 0. And, I know the word is and because they're connected in this manner. And X is less than 2. So, and implies where are they both true? They're both true in the middle. So we're looking on the interval from 0 to 2 only. This would be my working graph, and this will be my final graph. If I ever ask you to graph a scenario, you have to make sure you give me your final graph. You'll lose points if you just leave the working graph. Alright, so now what's actually going on at 0? Are they both true on 0? No, only the red one is true, but this one's true infinitely close, so I'll have an open circle on 0. Are they both true on 2? No, but they're both true infinitely close, so again I'll have an open circle. This is my final graph. Now I want to use this final graph to write my interval notation, so I read it from left to right. Nothing, 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 0. Open or closed on 0? Open. Up until 2, open, and nothing after 2. For part B, I have x is greater than negative 3. So it will be open and to the right. The interval notation will be open negative 3 to positive infinity. You can rewrite this inequality in this manner. X is greater than negative 3. Notice how the Pac-Man is still eating the larger value x, still eating the larger value x. So just make sure that inequality is facing the correct direction as you read it backwards. Sometimes you will be asked to solve an inequality. If this is true, and you multiply both sides of the inequality by a negative number, you will change the direction of the symbol. So that's what this bullet point here means. If you multiply or divide both sides of an inequality by a negative number, it will change the direction of the symbol. To solve this inequality, I have to keep this bullet point in mind, but besides that, it's going to remind me of solving an equation. So if I were to isolate x, I would just subtract 6 from both sides, and I would get x is less than 3. I did not change the direction of the symbol because I did not multiply or divide both sides by a negative number. So then I just plot my inequality, x is less than 3, and I write my interval notation from left to right. So from negative infinity to 3, open. Feel welcome to pause the video here and try B and C completely on your own. To isolate x in part B, I'm going to start by subtracting 8 from both sides. To divide both sides by a negative 3. Now here I divided by a negative, so I have to remember to change the direction of my symbol. Now I have x is greater than or equal to negative 4, so I'm going to include my boundary point because negative 4 is greater than or equal to negative 4. That's a true statement, so my boundary point will be true, and I'm going to shade to the right. Now that I have my graph, I can write my interval notation from negative 4 closed up until positive infinity open. I'm going to get the variable terms on one side and the constant terms on the other. I'm going to do this by subtracting 3x from both sides. I'm going to add 3 to both sides. I'm going to divide both sides by a positive 4. I'm dividing by a positive 4, so I do not need to change the direction of my symbol. 6 divided by 4 simplifies to 3 over 2. Graph it. 3 over 2 is equivalent to 1.5, or 1.5. Open on 1.5 and shaded to the right because I'm looking for all values greater than. So that would be open on my boundary point all the way up until infinity. Feel welcome to try this one on your own. You can get a common denominator all the way through, or you can multiply both sides of the inequality by the common denominator 6. I chose to do the second strategy, so I'm going to multiply both sides by 6. If I have 6 over 1 times 2/3 x, this will simplify to 2, so I'd be left with 2 times 2x, which is 4x, plus 6 times 12, which is 72. I multiplied by a positive 6, so I don't have to change the direction of my symbol. Now I have 6 times x over 6, which would just be 1x, plus 18 times 6 would just be the 108. Once I get to this step, it looks really similar to the problems from before, so I get my variable terms on the same side and constant terms on the other. I would divide both sides by a positive 3. Since I divided by a positive 3, I do not have to change the direction of my inequality symbol. Open on your boundary point and shaded to the left. Your interval notation would be from negative infinity to positive 12, open. This is called unbounded because it goes on forever in one direction. An inequality like this would be considered bounded because it has a stopping point on each side. If you have two inequalities joined by the word and or the word or, you'll be dealing with a compound inequality. And implies the intersection, or is the union. For and, it must satisfy both inequalities to satisfy the entire inequality or the intersection. For or, if it satisfies at least one inequality, it will make the union true. This inequality and this inequality are exactly the same thing. You can express them in this form or in this form. So you're welcome to expand this out if you want to. When I personally solve an intersection inequality like this, I tend to, first of all, realize it's an intersection. I know it's and, because I was able to condense the inequality without writing a word. Here, the variable that you're looking for, in this case x, must remain in this center. Block this left-hand side out to figure out what to do first. So if this were blocked out, what would you do to both sides of this inequality without taking the x from that side? So you would add 2 to both sides. So now, instead of just adding 2 here and here, I'm going to add it to all 3 sides. So I would get negative 5 is less than or equal to 5x is less than 10. And then from here, I would block this part out again and say, what would I do? Besides move the variable, I would divide both sides by 5. So that's what I'm going to do next. I'm going to divide by 5 here, here, and here. So I'm left with x in the middle is less than 2, which is greater than, x is greater than or equal to negative 1. I know this is and, so I have to figure out where are they both true. So I'm going to graph x is less than 2 first, and x is greater than or equal to negative 1. And implies where are they both true, so it looks like they're both true right in the middle. So they're both true on negative 1, both true in the middle, all the way up until 2. So I'm going to get rid of the working part. This is my final graph, and I can write my interval notation from there. Closed on negative 1, all the way up until 2 open. If the word connecting them is or, you have to actually write the OR. You can't condense it in this manner. So you have to actually write OR out. If you get a problem like this, you would solve each one of these separately and put them together with the word or on your working graph. So pause the video here, solve this, and play to check when you're ready. I'm going to solve this by subtracting 6 from both sides first. 2 minus 6 is negative 4. I'm going to divide by a negative 3. Remember, when you divide or multiply both sides by a negative, you have to change the direction of the inequality symbol. So it was less than or equal to, now it's greater than or equal to. To solve the right-hand one, I'm going to subtract 6 from both sides, and I'm going to divide by a negative 3. Remember, the word connecting them is or. So I want less than or equal to negative 1/3, or greater than or equal to 4/3. The word connecting them is or, and there is no overlapping portion, so my working graph and my final graph are the same, so I don't have to adjust this. I just have to read it from left to right to get the interval notation. From negative infinity up until negative 1/3 closed, union 4/3 to positive infinity. To solve this last inequality, you're going to solve each one separately and then condense with the word and using your graph. Video once you're ready to check your answer. I'm going to get the variable terms on the same side, so I'm going to add x to both sides. I'm going to subtract 3 from both sides. Divide both sides by a positive 3, so I don't have to change the direction of the inequality symbol. See if you can use these phrases to write an inequality. If you're having trouble whether to include the boundary point or not, I like to relate it to things that I care about. So let's try something like this. X is at least 3. So we know we're comparing it to 3. At least 3. We know it has to be bigger, right? But what about that boundary point? Could it equal 3? So you can compare it to something you care about, like grades. So if you need a C in the class, you need at least a 70. So a 68 would not be passing. A 71 would be passing. But what about a 70? Would a 70 be passing? Yes. So it would include the boundary point. So you can compare it to things that you care about to figure out whether that boundary point is true or false, or whether you should go larger or smaller. So play the video when you're ready. X is at most 3. So it could be 3, and it could be anything less than that, but it can never be more than 3. X is no more than 3. It can't be bigger than 3, but it could be equal to 3. X is no less than 3. So it could be bigger than 3 or equal to 3, but it could not be less. X is more than 3. So it can't be 3, but it has to be more than 3. X is at least 2, but less than 7. So what does that but imply? Is it or and? So if it's at least 2 and also less than 7, we're looking at this interval right here. So that implies an intersection. So X would have to be less than 7 and also greater than or equal to 2. Notice how I read that backwards. X is greater than or equal to 2. A student group has a budget of $4,500 for a field trip. The cost of transportation for the trip is $1,900. To stay within budget, all other costs, C, must be no more than what amount? See if you can write an inequality to set up this scenario, and then solve that inequality to answer the question. So what you spend has to be less than or equal to your budget. So to figure out how much you spend money on transportation and whatever other costs you have. And that has to be less than or equal to your budget, which is the $4,500. So you set up your inequality. Now you want to solve it. So I'm going to subtract $1,900 from both sides. So your all other costs must be less than or equal to this amount.